Alright, so what the voltage drop principle is saying is that whenever a voltage source like this drives a current like this across a passive element, which in this case we have a VR, we have a resistor, just R1, it experiences a voltage drop, right? So we know that the basic equation applied, which is as of now, is this V is equal to IR, right? And then, so now we are considering just this side. And we know this current is coming from this voltage source. This current here is coming from this, right? So clearly, what this says is that now that we know that definitely this current is passing through. We know definitely that this current I here is passing through this element, right? And then from the current division, there is no node here, meaning that the full current that is coming, this I here, this I here, no, this I here will be the same I flowing through this. Why? Because there is no node here, right? It's just a straight line through them. We've seen that. All right. So that means that at this particular junction, or when we consider just this resistor, what's happening is that this R is constant, right? And what again? I is constant, right? Meaning that this V that we're having here will be different from this V that we have. That's the voltage from the source, right? Yeah. So basically that's what we're saying. But then we see a drop because there's a reduction in the voltage that comes from the source, right? So if we are talking about something like that, this is what we are seeing. A drop means there's a decrease, and a decrease is sort of like a minus, right? So let's see. So what we're saying is that when this voltage here drives the current through this, the voltage that gets to this is not equal to the full of this, right? So if we're writing it algebraically, it means that this V here is equal to V1 plus V2, right? Yes. So that means if we are trying to find V1, let's say we are trying to find V2, let's go to V minus V1. So this is the basic understanding, right? But then we've considered this. That means that across the resistor R1, across this one right here, what we have is that we have V1 is equal to I, because the same current that's passing through them, which is the main current, right, which we have here, this here, right? And then we will have the resistor R1. The same will be a similar scenario for the resistor 2. The current passing through them are the same, right? So we have this R1 here repeating the same way, all of them obeying this equation here, right? This equation here. Okay, but then we will have R2 here, right? Yeah, so that's what we're saying. But then we're going to look at an example. Okay, so if we have something like this, and our aim is to find the current, let's see, is to find this R and then the current here, right? So clearly we know that the current flowing through these two are the same, right? Why? Because there's no branch here, right? There's no branch here. Yeah, there's no branch here, so the current flowing through the man is the same, right? All right. So then our aim is to find what? I and R. So clearly mean that if we are trying to find let's see, let's go back. The basic equation that we use is equal to IR, right? And then now we are trying to find this I here and R. Which one do you think we can find first? Which one? What do you think? So because these two resistors are in parallel, that will mean that we can use 10 here. Sorry, these two resistors are in series, so we can add them up directly. And so that will mean that we have still obeying this equation here, right? Still obeying this. That will mean that we have 10, right? And then the whole I is this, and then the whole R, what do we have? It's 3 plus R, right? Okay, so this is one equation that we have, right? And then again, because we have, this shows that we have two variables, right? I and R, so mean that we will need two equations to solve these, and then we get it directly, right? And then we can use another equation where, so here we are considering the whole circuit or the whole loop, right? So what it is that we consider all this, and we use this V is equal to IR, right? Yeah, and now what's happening is that we can just consider just one part of the whole thing, let's see, and get another equation, two variables, two equations, then we can solve, right? So now we consider this side, right? So let's see, that means that we have still obeying v is equal to IR. That means that we have 4 is equal to I, and then the R is what, just R, right? The two variables, two equations. So now let's see what we can do about this. So let's say this is 1, this is 2. Based on understanding, you can solve it every which way, but if you see what you need and then you try and find ways to use what you have to find what you need, then it's always simple for you, right? So let's see. So from 1 we have let's see, 10, let's go to 3I plus IR, right? Yeah, and then we have 4 is equal to IR, still remains, so let's keep that. Okay. So that moment, this means that we are using these two equations, right? So let's kind of make this 3, right? 3. This is 3, meaning that we have IR is equal to 4. We can put that in. That means we have 10 is equal to 3I, and then we have plus 4. Why? Because this here is equal to all this here, clearly, right? It makes your work easier. That means that we have 10 minus 4 is equal to 3I, and then our I, let's go step by step so we see what's happening. So if we have 6 here, and then we have 3I, and this will mean that we have our I to be 6 on 3, and that gives us 2, because it's current. Amperes, very important, because the unit is very important. We have amperes here, right? So that's what it means. And now that we have this, we can go back and use this and find our R, right? So we know 4 is equal to IR, right? And let's write this wall. This R here specifically is yeah, just it's only one variable, so that's fine. Okay. So that's 4 is equal to IR. So we have 4, and then we have I, which we found to be 2, and then we have R, right? So that will mean that we have our R to be equal to 4 on 2, and that gives us 2 ohms, right? Unit very important, 2 ohms. Yeah, so that's it, that's what we have. So what this means is that whatever problem that you have, we don't use the principles that we've been doing so far in isolation. You have to think through it and understand and know that, oh, at this point I have to use this, I have to use that to get what I'm looking for, right? But then let's go over one more thing. We've seen clearly that when it comes to a current division rule, or let's say when it comes to current, let's say we have two, let's use this, we have two passive element, this and another one like this, right? And then we have a current flowing in this direction. What it means is that because we have a current here, the current in this one here will be the same as the current in this one here. So if I1, that will mean that, let's say I1, this let's say 1, this is 2. This will mean that I1 is equal to I2. Why? Because they are in series, right? That's for that, right? But then if it happens that let's say the current is come from this side, we have a branch here, we have another branch here. This is this, and this is this. That will mean that, let's see, if this is 1 and this is 2, clearly I1, right, is not equal to I2. That's for current, right? But when it comes to voltage, right, when they are in series, right, so let's see, we have this, yeah, okay, this here, and then we have this here, and let's say this is 1, this is a 2, right? Just take this here, sorry, because it's voltage, right? So let's say we have a voltage source about, let's say here, let's put something, so this right, this is a voltage source. What it means is that because it is voltage, the voltage across 1 is not equal to the voltage across 2. Why? Because they are in series. But if they are in parallel, let's say we have a voltage source, this, and then let's say we have this, we have another one, this, right? It's connected this way, and we have our passive element here. What this will mean is that let's say this is 1, this is 2. the voltage across 1 is equal to the voltage across 2. Why? Because they are parallel, right? They are parallel, and we've seen that how to find whether they are parallel. That if you are able to go through the element without passing through any other thing, then they are parallel, right? So in summary, when it comes to current, so let's write it this way. And then we have voltage. When the elements are in, let's see, so let's write it this way. Okay. 9 minutes. Okay. Alright. So let's put them here. Yeah, just adding some other information. We're just summarizing this because when you understand this, it helps you to analyze your circuits better. So let's say we have a series here. If the elements are in series, right, or if the elements are in parallel, right? So for current, if the elements are in series, the current is the same. But for voltage, if the elements are in series, the voltage are different, right? As we've seen. Alright, and when the elements are in parallel, the currents are different, right? Because there will be some kind of split somewhere, right? And for voltage, if the elements are parallel, the current is what same. Yeah, so when you understand this and you're able to combine it with all the principles that you've learned so far, with all the rules, you're able to analyze every circuit that you have very well. With that being said, another way to solve this will be that if we are considering using the voltage drop alone, that would be to say we have let's see, so we have a voltage of 4 and then the voltage from the source to be 10, right? So that will mean that the voltage that we have across the 3 ohms resistor will be, because there's a drop after the voltage drive the current through the this R resistor here, right? So there's a drop after it drive the current there. So that will be, we have 10 minus 3, so minus 4, right? So 10 minus this 4 here, right? And that will be 6 volts, right? So now that we have the voltage across this one right here, it means that because they are in series, there is no current, the current didn't divide, right? There's no branches, the current didn't divide. So that will mean that we have the current across the R to be the same as the current across the 3 ohm resistor, right? So clearly we know that 3 ohm resistor, the current across it, using this equation starting with V is equal to IL, which is the basic equation at the moment, right? Mean that I will be V, I will be V on R, right? And this V is the voltage across the 3 ohm resistor, right? And this R here, we know it to be 3 ohms, so that will be here. We know the V across the 3 ohm is 6, and then the resistor, we know that to be just 3 ohms, right? So 3 ohms, and this will give us the current across the 3 ohm resistor to be 2 amperes. And clearly we've seen that the current across the passing through the R resistor and the current passing through the 3 ohm resistor are the same. Why? Because there is no branch here, so the current didn't split or anything. The current passing through them is the same, right? So that will mean that using our aim is, now we found what's the name, the current, right? We found the current. Sorry, we found the current. So that will mean the next thing to be is to find R, right? And then again, consider the same equation. At the moment, there's the basic equation that we use, and we're trying to find this R. So that R will be V 4 ohms, right? The voltage across the 4 ohms, and then the current passing through the 4 ohms resist, the R resistor, right? And then we know the current, the voltage across the 4 ohms resistor is what we found. It's already there. It's 4. There's no 4 ohms. We've not actually. So the current passing through the voltage across the R resistor, right? So this way. All right, we know that to be 4, right? And the current passing through, if I didn't file it, is same as this I. The current passing through I3, which is 2, and this gives us 2, and because we are dealing with resistor, 2 ohms. The unit is very important, right? Yeah. All right.